I'm going to move us right along to our final presenter of the series, and that is Thomas Balding, alongside his mentor, Dr. Rebecca Purvis. Would you like to introduce your intern?
Yes, thank you. Can you hear me? Okay, hello everyone. Thank you for staying till the very end. I'm very excited to introduce Thomas. He is a senior from Fort Lauderdale, Florida. He loves math and he loves physics, including quantum physics and space. He definitely went all in this summer learning about space weather. We had a lot of fun watching solar activity unfold before us in real time. At moments, it sort of felt like the sun was participating in the project and giving us really interesting data to look at, putting on kind of a show for us. Another thing about Thomas is that he really loves sharing what he knows with others. And so I'm going to stop talking now and I'm going to let him share his project where he learned about solar flares.
All right, so first I'm going to try and see if my microphone's working.
You sound great.
Perfect. All right. Do you want me to share my screen to show this?
Yep, you can do it, or I can, whatever you prefer.
All right, I think I will.
Great.
All right. Can everyone see this?
Yes.
All right, so I'll get started then. So for my project, I went into, mainly the causes and effects of solar weather, coming obviously from the sun, and, wanting to find ways to more easily predict, how solar weather is going to occur and what we can do to prepare. So I might as well get it out of the way. So a solar flare is an intense localized eruption of electromagnetic radiation that protrudes out of the sun's atmosphere. They occur in areas which are called active regions, or you can see them on the surface. They're usually called sunspots, and they're occasionally accompanied by something called a coronal mass ejection, which is the large kind of explosion looking thing that you see in all the videos of the sun and stuff. So next I will get into the solar cycle, which refers to the variation in the amount of sunspots on the sun's surface, as well as the variation in solar flare activity. Every solar cycle is approximately 11 years long, and the sunspots or active regions are directly proportional to the amount of observed solar flares. So currently we are in cycle 25, coming up on what is called solar maximum, which is when sunspots and solar flares are most common. So the goal of the research that I've been doing is to try and analyze these solar flares so we can more accurately predict when a large solar storm is occurring, or when Earth might be affected in a significant way. So ways that solar flares have affected the planet in the past include things like radio blackouts or electrical power outages, even damage to spacecrafts or satellites. In 2003, around October, we lost half of all of the satellites orbiting the planet to a large solar storm that we were not prepared to, experience. So I think being able to predict solar storm occurrences will be beneficial to not just, studies in heliophysics, but also all sorts of astronomy, because if our space telescopes are being taken out by the sun, every cycle, then we're not going to be able to do much with them. So predicting solar flares is actually very hard because it is a very complex behavior that's governed by a lot of different variables. The sun has a very complex magnetic field, and it makes it difficult to create accurate predictions. So my strategy was to understand the statistics behind the occurrence of solar flares and try and compare it to readings that I've been getting from solar maximum years. So for my methodology in experiment, my goal is to collect data from Earth orbiting satellites, X-ray flux data from GOES satellites, and EUV data from the Solar Dynamics Observatory. And then afterwards, I did a lot of statistical analysis on peak X-ray flux. And my main goal for this was to try and recreate a self-organized criticality graph to show how the occurrence of solar flares, in specifically with reference to their energy level and the frequency at which solar flares of that energy occur, are related. So you can see over here, can you guys see my cursor?
Yes.
Okay, so this graph I'm over here is kind of showing the relationship between those two things. So that was something I was attempting to recreate throughout my project. So these were a few of the databases I used. The Integrated Space Weather Analysis, or the ISWA, was very helpful in visualizing a lot of solar data. They have a lot of useful different graphs and settings where you can pull up videos of the sun from space telescopes to try and observe your satellites. It also helped me get a lot of locations of solar flare occurrences from the sun's surface. The Database of Notifications, Knowledge, and Information, or the Donkey, was very helpful in getting things like coordinates of, where solar flares are occurring on the sun's surface, as well as collecting data about solar flares themselves. And then finally, the Interactive Multi-Instrument Database of Solar Flares was very helpful in helping me quickly get the data I needed, very efficiently, regarding to solar flare class, which is a measurement of solar flare energy. So these three databases were all very helpful in my research. So results of my experiment. So first I'll go over some solar flare locations. These were all recorded in the month of May of this year. So the goal of this was to see if there's a certain area on the sun's surface where solar flares are commonly coming through. So on this graph here, all these little points that have a number near them corresponds to the date of the month. So for example, this one over here occurred on the 20th of May. And through this, you can kind of tell where some active regions are and how they've moved. So for example, there was one over here which spit out a lot of flares on the 18th, moved over on the 19th, the 20th, and then kind of died out. And there's maybe another over here with a bunch of solar flares on the 8th and 9th of the month. Something else you might have noticed is that these flares seem to be occurring in bands on the, on the north and south side of the sun. So this is a phenomenon that occurs with the solar maximum. Flares will come in, and as they get closer and closer to the maximum, get closer and closer to the equator of the sun. So these bands will kind of move in from the top to the bottom, and then this band down here will move from the south pole up to the equator. So active region number 1331 was a particularly active sunspot that I've observed coming from, May and June of this year. Over here is a chart of every event that has been identified with it. Had over 20 flares spit out of it between a power of M1 and M8.9 over just 6 days. And just to get it out of the way now, what I mean by solar flare power in this classification is, solar flares are classified with, numbers and letters like this over here. So for example, M1 is, kind of the median. It goes from C, it goes C1, C2, 3, 4, 5, all the way up to 10. And then it switches to M, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then X's, which are the most powerful. It's on a, power rule scale. So it's all, for example, M1 has a power or, workload of, 1 times 10 to the negative 5. C's are times 10 to the negative 6, and then X's are times 10 to the negative 4. So it works on kind of a logarithmic scale there. So here is a video of the sun's surface where you can view this active region. You'll see, it's near over here, and you can see all the loops, the magnetic loops coming off of it that's connecting it to other locations. You can see a few flares coming off of the sun, like over here. It's very interesting. One of my favorite parts about the project was getting to look over videos like this. Oh, all right, so here's some of my next graphs. So here's the original graph I was trying to recreate. And this is the graph I made with data from May and June. It was my first attempt and admittedly quite flawed. So one of my main focuses was trying to fix this and see where I went wrong here. So the reasoning for this is because I used a really small data set. I only took flares from 2 months of this year, May and June, while most of these graphs will incorporate data from an entire 11-year solar cycle. So taking that into account, I kind of buffed up my data set here. I included data from solar maximum years 2003 and 2014. You can see that both solar maximums are pretty consistent with each other in terms of their flare distribution. Again, this is a graph comparing the peak energy of each flare with how many times a flare of that energy has occurred. So this is on a logistic scale on the X and Y axis. And, again, this is looking a lot better than my first graph because now my data is seeming more consistent. So analysis of this data has been really interesting because I have had repeatedly a spike, a big spike occur over M1 flares that, according to my other sources, isn't normally there. So a big point of this project was figuring out why this spike keeps occurring. So first of all, the reason the spike is there in the first place is because I've been recording an increase in M1 flares during the solar maximum year. So the way it should go is that this should just come down here and go through. It should be the less powerful the flare gets, the more common flares like it are, but this hasn't exactly been consistent. Some more details about the spike is that it has been consistent as of the past 3 solar cycles. It's been occurring in every solar maximum year, 2023, 2014, and 2003. Like, in 2003, I mentioned earlier, we had that massive solar storm that took out some of our satellites. So this could have even been a potential cause of that. However, it is also possible that this is a normal part of the solar cycle. However, this conclusion would require more data from past cycles. Unfortunately, my sources only have data from after 2002, so I would have to look in this a bit more deeper to find older data and do analysis on that. But still, I think this does show that this, phenomenon is fairly consistent. In terms of reasoning why it hasn't been seen much before is because, again, graphs like this will usually take in data from an entire solar cycle. So I think this occurrence in my data is because my data set was more precise, focusing on the most active time frames of the sun. So to conclude on my research, it was a lot of fun, really. I loved having the opportunity to work on something of this magnitude and getting to work with NASA for my first internship. My mentor, Rebecca Purvis, has been incredible with working with me and, helping me adjust our goals as we got increasingly stranger and stranger data from the sun. And before I finish up here, I want to go into a topic that could be looked in a bit deeper. These are called sympathetic solar flares, which are solar flares that are caused by another solar flare. So over here in this image, you can see all these magnetic loops connecting active regions together, like here and here, a whole bunch coming off of this one. So I think studying these sympathetic solar flares could also help get a better understanding of solar flares and solar storms from a statistical standpoint, because if we understand these parts, then we're going to be able to predict these solar flares popping out by looking at the sun's activity as a whole and predicting which flares could cause a sympathetic event. So that does conclude my presentation. I hope it has been entertaining, and I hope that you guys have enjoyed it as much as I've enjoyed working on it.
Thanks, Thomas. Great work. I was wishing our other N3 team member, Laura Pedicolis, was here because she's a heliophysicist. She would have loved to listen to your presentation, but I'll have to tell her to watch the recording.
Oh, that's unfortunate.
Yeah, so I've been learning a little bit about solar flares because of our work with the high school curriculum that we were doing this year through the N3 project, which is the other thing we do besides the intern program. But I had not heard of sympathetic flares, so that was really interesting to me. Thank you so much.
Welcome. It was a joy to work on it.
Do you think you're going to continue your work?
Most likely.
Michael,
I hope so. Yes.
awesome. Michael was wondering how far back the data goes. Like, how far back can you look at cycles?
Right. So, right now we're on solar cycle 25. So, all the data from my sources, the furthest back I was able to get from is 2002. I would love to find a database with some older data, though, to confirm some of my theories. Unfortunately, when looking at and trying to collect data from things like this, it just comes down to we've only had the technology to look at the sun and get data from the sun with this much accuracy for so long. So, really, we're just kind of beginning in terms of data collection. So it will be really interesting to see in the future when we do have more precise data on this, what new things keep popping up and what we keep learning. Because, it was interesting. I've never heard of, a spike in a certain type of flare before, and I couldn't find any mention of it anywhere else. So, it's just a joy, really.
Yeah. It'd be so cool if it stays real when you get more data. But yes, there are a lot of funded citizen science projects for the upcoming eclipses, including one led by our very own Laura Pedicolis, which is Eclipse Mega Movie 2024. So if you're on the line of totality, you can be one of the observers that takes pictures of the sun with special equipment and puts it all together in a big movie that goes along the whole line of totality.
All right. Well, I'm sorry we went so over time, but these presentations were incredible.